Hello there, trigonometers and pre-calculators. In other words, people in trig and pre-calc. So we are looking at the double angle identities today. And after this, I'm going to go on to make a video or two on the half angle identities, which are pretty much used side by side with double angle identities very often. But first off, we've got these guys that we're using. And this is the second of two videos addressing the types of problems that we deal with double angle formulas or double angle identities. Sometimes they're called double angle properties. This second word can be lots of things, but double angles. So here is one type of problem. It says use the given info to find the exact value of the expression, and it gives me some info. I want you to remember that when we are given information like this is telling me where I am in the coordinate plane. It's telling me about a quadrant. The reason I would need to know about a quadrant is I need to know where I'm going to draw my triangle. So this is kind of a hint that I'm going to be drawing a triangle. Now there's a bunch of different ways they can tell me what quadrant to draw my triangle in. This is saying we want to draw it, remember zero's out this way, between 90 degrees and 180 degrees, which is a way of saying second quadrant. Other ways of saying second quadrant, they could just say in quadrant 2. That's one way. They could use radians instead of degrees to say the exact same thing. That's how it would look in radians. Or they could tell me something about another trig function's value in this quadrant. They could say that. They could also say this. Either one of those. Now, what that tells me is they're saying, hey, you want to do this in a quadrant where the sign is positive. The reason I know the sign is positive is because I don't see a negative sign there. So a quadrant where the sign is positive, that means one of these two. Remember, sign is like a y value, so it's up here or up here. So sign is positive, and if they tell me the tangent's negative, the two places the tangent's negative are second quadrant and fourth quadrant. So if sine is positive here and here, and tangent's negative here and here, it has to be second quadrant. Or they could have instead, they could have said the sine is this and the cosine is negative. I'm trying to keep my cat from walking up underneath the dock can. So cosine is negative here and here. So if we have sine is positive, that tells me two quadrants. Cosine is negative. The one that both of those are true in is second quadrant. So there's several different ways they could tell me that. This time they used this one. What that says is go to the second quadrant, draw a segment out into it. It doesn't really matter where. Okay, we're going to use the information we were given. We're not worried about it visually. We're not going to use our eyes to tell us how this works. And then go from the end of that segment to the x-axis, and there is your right triangle. Now, we are being told the sine is 20 over 29, going back to SOHCAHTOA, the good old right triangle trig. Sine is opposite over hypotenuse. So that's the SO of SOHCAHTOA. Okay, sine is opposite over hypotenuse. So this must be the opposite, and this must be the hypotenuse. And if this is this, we always put the theta closest to 0, 0. So opposite is here, hypotenuse is here. Let me just point out, if this was a value that was negative, if it was a fraction that was negative, we would always put the negative with either the horizontal or the vertical. The hypotenuse is never going to be negative on these. We don't ever make the hypotenuse the negative. Just letting you know. All right, so I'm supposed to find this tangent of 2 theta. So I go to my formula and I say, okay, tangent of 2 theta is all of this. So I don't have to know sine or cosine to find this. I need to know the tangent. If I know the tangent of theta, I can plug in and find the tangent of 2 theta. So tan of 2 theta equals 2 times the tangent of 1 theta over 1 minus the tangent squared of theta. So I need to find the tangent of this guy, which means I need opposite over adjacent, which means I need to find this missing side. Okay, this is a Pythagorean triple. Just checking myself to make sure I don't lose my mind. Well, I thought it was. Yeah, it is. And this will be 21. Pythagorean theorem tells me that if this is 20, that's 29, hypotenuse is 29, the other leg has to be 21. So the tangent of this theta, and I'll just write it up here, is opposite over adjacent, which is 20 over 21. So now I'm ready to plug into this formula and simplify, and I'll have my answer. So 2 times the tangent of theta, that's 2 times 20 over 21, all over 1 minus the tangent of theta squared. So that's 20 over 21 squared. So remember, 2 is the same as 2 over 1. So that's like 2 over 1 times 20 over 21. So that's 40 over 21 on top, all over 1 minus 400, excuse me, over 441. That's what I get when I square that. And when we add and subtract fractions, we need common denominators to do it. So this is what I'm going to do. And from here on out, I'm just simplifying. Pretty much from the second I plug it in, I'm just simplifying. So it's all just kind of plug and chug, numerical calculations here. The way we divide fractions is and let's go ahead and write it this division first. That's what this means. This means top divided by bottom. That's what every fraction means. And the way we divide fractions, remember, is that we change this to multiplication and then flip the second fraction. In other words, we multiply by the reciprocal. So that gives me this. Okay, 441 is 21 times 21. So I'm going to go ahead and rewrite it like that so I can cancel out a set of 21s. And that gives me 420 over 41. And I think that's as far as I can take it. I believe 41 is prime, so there's nothing else we could do unless 41 goes into 420, which it won't because it goes into 410. That means that is my final answer. I did not promise it would not be messy. Okay, so what we're doing is actually pretty simple in terms of we find the tangent and we just plug it in. But once we've plugged it in here, we have a little bit of a mess in simplifying it. All right, next type of problem I want to look at with double angle formulas is problems that ask me to write the expression as a sine, cosine, or tangent of a double angle, then find the exact value when they give it to me like this. And if you've watched my videos about the sum and difference formulas, you'll know that this is not an uncommon thing, is for them to give us an expression that really matches the right-hand side of the formula. It matches one of these. And we have to recognize that and use the formula or the identity going from right-hand side to left-hand side, which is not usually the way we would look at it, but it's not like there's anything wrong with that. If two sides of if you have an equation, if you have two things that are equal, then it works in either direction. You could start with one and go to the other. So what we have to do here is we have to be familiar enough with the formulas that we see that this looks familiar, that this is 2 times the sine of something times the cosine of something, and I've been doing that right here. So 2 times the sine of an angle times the cosine of an angle is the same as the sine of 2 times that angle. So it's going to be the same as the sine of 2 times, and here my angle is 112.5, which is the sine of 225. It says, then find the exact value. Well, thankfully, 225 is an exact unit circle location. It's right in the middle of the third quadrant, where we go to the left, root 2 over 2, and down root 2 over 2 to get there. And this is the sign. The sign is the y value. So that is my answer. All right, next two problems are very similar. We're given one to start with that looks like the right side of one of these formulas, one of these identities, and we have to recognize that and use the identity. So this time it's cosine squared of 30 degrees minus sine squared of 30 degrees. So again, I look at that and I think, hey, that looks familiar. Haven't I been doing something with cosine squared minus sine squared? And the answer is yes, I have, if I've been doing double angles with cosine. So cosine of 2 times the angle is the same as cosine squared of the angle minus sine squared of the angle. So here my angle is 30. So this is cosine of 2 times the angle, which is 30, which is cosine of 60. And again, that's a very nice unit circle value. 60, 30, 60, 90 triangle goes out that way, out 1/2 and up square root of 3 over 2. My point is 1/2 root 3 over 2. Remember, it's the x value that is the cosine. So my answer here is 1/2. All right, last one like this, and that's also the last problem we're going to do on this video. It looks a little bit yuckier, but really when you're doing them this way, where you're starting with the sort of more complicated side of the identity, as soon as you recognize that it goes with a particular identity, you can make it easier pretty quick. You can make it a simpler situation. So here, I'm having to recognize that this is 2 times tangent of some angle over 1 minus the tangent squared of that same angle, and that is something that I've seen before, and the place I've seen it is right here. 2 times tangent of an angle over 1 minus tangent squared of an angle equals tangent of 2 times the angle. So the angle here is pi over 8. So this equals equals the tangent of 2 times the angle. 2 times pi over 8 is the same as 2 over 1 times pi over 8. So that's 2 pi over 8. Simplifies pi over 4. So I'm being asked to find the tangent of pi over 4. Pi over 4 is in the middle of the first quadrant. It has a cosine of square root of 2 over 2 and a sine of root 2 over 2, and looks like this. And remember that tangent is sine over cosine. So the second coordinate over the first coordinate. So that's going to be square root of 2 over 2 divided by square root of 2 over 2. I really didn't even need to write that because anytime you divide some number by itself, you get 1. And that's my answer. I hope this has helped. Thanks for watching, and I'll see you next time.